Hello, and welcome to this ITCS long recorded talk on downward self-reducibility in TFNP. My name is Daniel Mitropolsky, and this is joint work with my co-authors Prahladh, Harsha, and Alon, Rosen. And this work actually emerged through a series of conversations that Prahladh and I were having with Alon when we were visiting him in Milan. And so actually this presentation is going to mirror our conversations and how we would realize something and then ask kind of the next obvious question and figure that out or not. And so it'll sort of mirror the development of this visit and how we got to this work. So what is downward self-reducibility? Sort of a reminder from this, you may have seen this definition a long time ago. A language L is downward self-reducible, or DSR, if there exists a polytime algorithm A deciding whether a string X is an L with an oracle for L, but on subqueries that are strictly smaller in length than X. Okay, so here are some examples. SAT is DSR, and here's a very simple proof sketch. Given a Boolean formula on n variables, x1 through xn, we're going to query two subqueries at most. First, we'll query phi, where we set the first variable x1 to 0. So what that means is we go into the formula, and everywhere where x1 occurs, we replace it with 0, and then simplify the formula. So if something is an and of x1 and another variable, well, we'll set that to 0 and remove that clause, and so on. So we remove it everywhere, and for this reason, this subquery is actually going to be smaller in length than the original phi. Okay, and if that's true, we return true. But if it's false, we do one more subquery, and it's the one where we set the first variable to 1. Okay. Now here's another proposition. Not just SAT, but in fact TQBF, or true quantified Boolean formulae, the PSPACE complete problem, is DSR. All right, and the proof is the same. The proof is that if phi begins with, let's say, all over x1, well, then we'll query two subqueries. We'll query the one where we set x1 to 0, and we'll query the one where we set x1 to 1, and go into the formula and actually remove x1 everywhere, thereby shortening the formula in each case. All right, and analogously for if it begins with an existential quantifier. Great, so those are two problems that are downward self-reducible. And several other NP as well as PSPACE complete problems are DSR. But there are NP and PSPACE complete problems that we do not know whether they are DSR, and we'll talk more about that later. But we know that conversely, if a problem is DSR, a problem here again means a decisional problem, a language is DSR, then it is in PSPACE. Interesting, and the proof of this is very simple. Because it's DSR, it has a very inefficient recursive algorithm where you query smaller strings and smaller strings and so on, but it is polynomial space. So you can kind of work that out. But what does it mean? What does it mean if a complete problem of a class C has a property P? And having the property P places you in C, right? Having the property P doesn't mean that you are complete for C. If that was the case, you would have a property P that is equivalent to completeness in C, right? So one consequence of having these two conditions is the following, all right? The consequence is that PSPACE is hard, which means there exists a hard language in PSPACE, where hardness can be in any sense, either worst case or average case with respect to sampleable distributions or computable distributions, whatever you want, is equivalent to a DSR language being hard, with hardness meant in the exact same sense. Okay, that's sort of one interpretation of having complete problems of a class have a property P, as well as that property imply membership in the class. All right. So in other words, like you can characterize hardness of PSPACE instead as hardness of DSR languages, which I think is quite neat. Now, in most of this talk, we will be talking about and interested in search problems. So what are search problems? They're not decisional languages where we have to output 0 or 1, but outputs can be strings of arbitrary length, but in general polynomial length. So here's an important definition. FNP, for functional NP, is the class of efficiently verifiable search problems. Okay. Whereas TFNP is the class of problems in FNP that are total. And total means that for every possible input string, there is at least one solution that is accepted by the verifier. The verifier is the one implied by the definition of FNP, the one that verifies solutions. So an example, here are two important examples. One is FSAT for functional SAT. That's the problem of finding a satisfying assignment to a Boolean formula, right? It's an FNP. We can efficiently verify a candidate solution, but it's not in TFNP because there are unsatisfiable formulae. right? Another example is factoring. Given an integer n, a solution is either the word prime, if n is prime, and note that we can efficiently check if that's the correct solution, or its set of non-trivial factors. Okay? The problem factoring is in TFNP, because for every input string, there is a solution. Now, if you've seen or heard of TFNP before, you may have seen various problems and subclasses that have sometimes long abbreviations beginning with P, like PLS, PPP, etc. All of these are actually come from a very simple idea, right? Suppose you have an existence principle or a proof of existence of the following kind, okay? You have a proof of existence which says that for any instance of a certain object, for any circuit, for any graph, for any integer, there exists an efficiently verifiable solution for that instance. Well, then such a principle automatically gives you a problem in TFNP, okay? And this problem will be interesting if that principle, that existence principle, doesn't yield an efficient algorithm for finding a solution, because otherwise it would just be in functional P. So for factoring, for example, the existence principle is the fundamental theorem of arithmetic, that every integer has a finite set of factors, or is prime. But the proof of that doesn't give you an efficient way to find the factors of any integer. Great, so that's sort of, these kinds of existence principles are what give rise to all of these classes you've seen before, like PLS and PPAD, and so on. Now, in this talk, we'll mostly be interested in one, which is local search. So the local search principle is the following combinatorial existence principle, all right? It says that if applying some sort of efficient step that increases on an objective on a finite domain, if you have a step like that you can apply that increases an objective in a finite domain, then a local optimum must exist. Okay? So it's a simple sort of basic set theory principle, because you can only apply the objective increase or finite number of times on the finite domain. So it gives rise to the following search problem, which we will call iter with source. Right? So this is a concrete problem now. So given as input a successor circuit under some fixed representation of circuits, a successor circuit S from n-bit strings to n-bit strings, as well as a source string S, such that when you apply the circuit S to little s, you get something that's bigger than S. So we'll mean bigger and less than as lexicographically bigger than throughout this talk. And the solution is to find another string V such that when you apply S to V, you get something bigger than V. So S did increase when applied to the point V, but when you apply S to S of V, well, then that string is less than or equal to S of V. So you found a local optimum. That local optimum was the point S of V. Okay. So PLS is the class of search problems that are polytime reducible to iter with source. Now, if you know PLS or TFNP from before, you might say, wait, this isn't the original complete problem by which PLS is defined. And that's true. But it's not hard to show that this is also complete for PLS. We'll define it like this for now. But we'll see other complete problems for PLS in a bit. Now, let's take a closer look at this problem iter with source. So I've just copied and pasted the definition here. What we're going to do is we're going to denote by S sub I the circuit you get by setting the first input bit of S to I, where I is either 0 or 1. So you set the first input bit to 0 or 1, and then you propagate that effect throughout the circuit. What do I mean by that? I mean, you feed forward through the layers of the circuit. So for example, if there's an AND gate and now you have a 0 feeding into the AND gate, well, then you can replace that AND gate with 0, right? And then propagate it onwards. Or if you had an OR gate, then you can replace it by the other input, just directly feeding into wherever that OR gate fit into, and so on. A concrete definition is given in the paper. It's very intuitive. So you propagate it, and then you remove the last output bit. And when you propagate, you also remove any constants and everything at the end. So the point is you get a circuit that is strictly smaller than the original circuit you started with. Okay. So consider the following oracle algorithm for solving iter with source. All right. And again, for iter with source, you have the successor circuit and a source string as input. Now, if the source string has a leading 1, well, then we have a source that is in the second half of the domain. So then we can just query S sub 1, where we set the first input bit to 1, with the source being the first n-1 bits of S. Because already there's a source in the second half, so we can just look for a sink in the second half, and that's a smaller instance. Okay, but otherwise, we're going to query S sub 0, as well as with the source being the first n minus 1 bits of S. Now, two things can happen. One is that this either gives you a solution to the original instance, or it'll give us a false solution. But if you think about it a little bit, if you pause this talk or go to the paper, it's all explained. But what is a false solution? A false solution is something that wasn't actually a local optimum. And the only way that could happen is if it left the subdomain that we queried on, so the first half of the input strings. So in other words, if you get a false solution, well, then this actually would give you a string S prime with a leading 1, such that S applied to S prime is greater than S prime. But then you have a source in the second half of the input strings, right? So then you can query S sub 1 with S prime, the first n minus 1 bits of it, and get a solution to the original problem. Okay. So what does that all show? That shows that iter with source is DSR. Very interesting. Now, we have to be a bit careful here because we're talking about DSR for search problems now. So let's just review the definition in this context. We say that a search problem R is DSR if there is a polytime algorithm A solving an instance X with an oracle for R, but on subqueries that are strictly smaller in length than X. Now, here's the extra part. And that succeeds, so A succeeds given any solutions to the subqueries that it queries on. Because in the decisional landscape, the only possible solutions are 0 and 1, but here there could be many solutions to the search problem. Given any of them, A needs to succeed. Okay, and so iter with source is DSR in this sense. And so the natural question we asked when we realized this is, are other problems in PLS DSR? And so the answer is sort of. So here's the original iter problem. And in this problem, it's exactly the same, except we're not given the source as an input to the problem. Okay. Instead, we're given the successor circuit such that when you apply S to the 0 string, it outputs something greater than the 0 string. So in other words, the 0 string is a source. And it's the same problem otherwise. You have to find a V that at V, S increases, but it doesn't increase at S of V. And now this problem is also PLS complete. But despite our attempts, it is not clear how to show that this problem is DSR in the way I previously defined. Why not? Well, what breaks down in the proof, if you try to sort of do the same proof, is that after the first oracle query on the first half of the domain, if you got a false solution, what did that mean? It meant that we got an S prime with a leading 1, such that S applied to S prime is greater than S prime. In other words, it's a source in the second half of the input strings, and that's great. But the problem is that the first n minus 1 bits of S prime might not be the 0 string. So it doesn't actually match the input representation of the iter problem. And so we thought about this, like, well, can't you just like shift all the inputs, like shift them mod 2 to the n over 2 or something like that, so that this string S prime becomes the 0 string, but that actually doesn't work, or at least we didn't figure out how to make that work. But it is downward self-reducible in a different way, all right? It is downward self-reducible in that we can reduce to smaller instances and smaller in the following sense, that they have less input and output bits. So that's going to lead to the following definition. So first of all, a circuit problem is a search problem where the input is always interpreted as circuits. So again, we fix some standard representation of circuits a priori, circuit C from n bits to m bits. Okay, so we say that a circuit problem R is circuit-d.s.r if there is a polytime algorithm A solving an instance C from n bits to m bits with an oracle for R, where for each subquery of the following form, C prime sub I, which just means there can be multiple of them, from n prime bits to m prime bits, we have that the sum of n prime plus m prime is less than n plus m. In other words, the subqueries have less input and output bits overall than the original circuit. Okay, and we also say that a problem is circuit-d.s.r with poly blowup if the subqueries C prime are at most the original circuit size of the original circuit representation plus, so additively more, polynomial in n and m. Okay, and so we have that the previous problem iter without the source provided is circuit-d.s.r with poly blowup, even though we can't show it's d.s.r in the strict sense. Okay, and the reason is that we shrink the number of input and output bits, but the actual circuit itself grows a little bit. Now, what about other PLS complete problems? So here's sort of the most canonical one that if you've seen PLS before, you've probably seen that class defined through this complete problem, sync of DAG. In sync of DAG, we're also given the successor circuit from n bits to n bits. such that when applied to the zero string, it's not the zero string. So zero string is a source. But we're also given the valuation string from n-bit strings to numbers between 1 and 2 to the m, just some maximum valuation. And we have to find a v such that s applied to v isn't v, but either it's a sinc, so s applied to s of v is s of v, okay, or we found a local optimum with respect to this valuation. So v applied to s of v is less than the valuation of v. If this isn't so important if you haven't seen this before or didn't internalize this definition when I said it, but the point is that this problem is PLS complete, and we show that sinc of DAG is also circuit-d.s.r with poly blowup. Once again, we don't know how to show that it's d.s.r in the strict sense of shrinking the full input size. And we show circuit-d.s.r with poly blowup for some other PLS complete problems as well, but these are just the most important ones. So, what's the next natural question we asked ourselves? Great, we've shown PLS, d.s.r or circuit-d.s.r for these PLS complete problems. The question is every PLS complete problem d.s.r or circuit-d.s.r? And the answer is we don't know. And we don't know because we don't really know how to show something like that. And one of the main reasons is that d.s.r is a property that is not preserved under polynomial time reductions. And it's a very simple reason, because when you apply a polytime reduction, the instance you get of the problem you reduced to could have blown up. It could have become like square the original size of the original instance. So then even if that's d.s.r, you won't be able to shrink it down enough to make the original problem d.s.r. So somehow it doesn't work. And in fact, the analogous problem in the decisional landscape is also open. So it's open whether every NP or every PSPACE complete problem is d.s.r. So we sort of don't know, but it's an interesting problem. But then here's the next natural question. So we said, okay, we don't know that. Well, the other natural question is the converse. Is it true that every d.s.r problem in TFNP is in PLS? And it turns out that the answer is yes. So we proved the following theorems. We proved that if a problem in TFNP is d.s.r, then it is in PLS. And we also prove, and this is sort of comforting, that if a problem in TFNP is circuit-d.s.r with poly blowup, then it is also in PLS. So for purposes of, inside of TFNP and membership to these classes, d.s.r and circuit-d.s.r are both good. They both give you membership in PLS. So what does this mean again? Remember this thing about properties and complete problems. What does it mean that there are complete problems in PLS that are d.s.r and d.s.r guarantees membership in PLS? Well, we can rephrase it with the following corollary. We know that if PLS is hard, either in the worst case or any average case sense, that is true if and only if a d.s.r problem in TFNP is hard, with the same notion of hardness. So we've given a new characterization of hardness of the class PLS, which has to do with local search. Great. So here's kind of a very quick sketch of this theorem that d.s.r implies PLS. So if a problem R is d.s.r, then it has a very inefficient recursive algorithm. And it's the obvious one. What you do is you run the Oracle algorithm recursively. So on all the Oracle subqueries, you just run the algorithm again and so on. It's very inefficient. But generally, here's the interesting thing about TFNP complexity. And this is something Pavel Hubacek told me some time ago, and I've kind of been repeating it ever since. But I do want to give him credit for this observation that reductions to TFNP problems are all about exploiting inefficient but very structured algorithms. So these algorithms would be too inefficient to show that these problems are in anything other than like TFNP subclasses, because they're inefficient, but they have some structure to them. So they give you a reduction to PLS or PPAT or one of these problems guaranteed by an existential argument. So the idea to this reduction is just to simulate the inefficient recursive algorithm as a walk on a graph. All right, and the nodes of this graph are just going to be the states of the inefficient algorithm. So what do we mean by that? It's the list of the subqueries so far with the solutions for each one, except for the last subquery issued, for which, we append the subcomputation of the recursive algorithm on that last subquery. And it sort of goes down like that. And the details are in the paper, but this very simple idea allows us to show that d.s.r implies membership in PLS. Great. So now let's kind of change gears a little bit and go back to talking about factoring. So let's recall the factoring problem. Given an integer n, a solution is either all of the non-trivial factors, and this time we're going to require that they're provided in decreasing order, or their word prime if n is prime. All right. So if you think about it, our results already imply that if factoring is d.s.r, than it is in PLS. And this is interesting because it is unknown whether there is a downward self-reduction for factoring. Is there an efficient algorithm for factoring that works by querying smaller numbers? Unknown, interesting, and if it were true, it would be in PLS, which would be surprising, and I'll touch on that later. But here's something else. In this problem factoring, solutions are also unique, right? Factoring isn't only in TFNP, meaning that for every input string, there's an output, but also those outputs are unique because we require this decreasing order thing. So we can strengthen our results. What we found is that we can actually strengthen our result for DSR problems in the class TFUP, which is just the problems in TFNP with unique solutions. And I'll show you exactly what that result is in a second. So this is sort of the most confusing slide of the talk, but it will all make sense. There's a very important problem in the study of TFNP, especially the crypto TFNP, called sync a verifiable or verified line, or SVL, right? And this problem, we're given the successor circuit as before, as well as a target integer t. And we're going to try to find the tth node you get by applying s t times. Now you're also provided a verifier circuit v, which takes in an n-bit string as well as a number from 1 to t in output 0 or 1. And it has the following promise. So SVL is a promise problem. It's a promise problem. The promise is that v applied to x and the number I is 1 if and only if this x is what you get by applying s I times to the 0 string, which will be our source. Okay. So, and the solution to the SVL problem, it would be the unique string v such that v is the tth node in this line. In other words, that v, the verifier applied to v and the target t gives you 1. Okay, so once again, v would be s applied t times to the 0 string. So SVL is a promise problem, all right? And it's not even in TFNP. Given an instance, so you don't, it's not guaranteed to have a solution because the promise might be false. But a very clever idea from the field of reversible computation called the pebbling strategy can be used to transform valid instances of SVL into a problem called unique end of potential line, which is in TFNP. There's a line of papers showing this, and the idea is very neat and elegant and has to do with reversible computation. So I invite anyone interested to look at that. And if I had time, I would present it in this presentation, because I think it's very nice. But this problem, unique end of potential line, is in a class called CLS, which we now know is actually the intersection of PLS, which we've been studying in this presentation, and another very important subclass in TFNP called PPAD. So this class is very, very low in the hierarchy of classes of TFNP. It's very, very down low. And there's a rich line of work which shows hardness in TFNP from various cryptographic assumptions. And you may have seen these papers showing hardness in TFNP, or sometimes they'll say showing hardness of Nash equilibrium or something like that from IO or from discrete log now, or like from different things, from different kinds of succinct non-interactive arguments of knowledge and so on. All of these crypto assumptions or hardness assumptions showing hardness in TFNP. All of these papers are actually constructing hard instances of this problem, UEOPL, unique end of potential line, via constructing instances of this promise problem, SVL. So kind of an aside is that it's interesting that all of these results we have about connecting crypto hardness assumptions to TFNP hardness, all of them have to do with constructing SVL instances, which give you hard TFNP problems very, very, very low in the hierarchy. So these assumptions are very strong and give you hardness of a problem that's very, very low. And that's how they all work. And our result is no different. So what we show is that if there is a problem R in unique TFNP and it is DSR, then it is reducible to sync a verifiable line, right? And hence, in particular, to this problem, unique end of potential line. And so a corollary of this is that for any unique problem, such as factoring, if it has a downward self-reduction, and in fact, we can strengthen this a little bit, if there is any algorithm for factoring by creating numbers that are smaller by any multiplicative constant, okay, then factoring is a unique end of potential line. But this problem is in CLS, which is once again PLS intersect PPAD. So this would really be a big deal, right? And this sort of, here's a schematic, a simplified schematic of TFNP. And the reason this would be so surprising is because factoring or factoring star here means versions of the factoring problem, are known to be in two classes that are sort of high up here called PPP for pigeonhole principle and PPA, which are parity argument. And both of these classes contain the subclass PPAD. People have been working for a while on showing that factoring is in the class PPAD by kind of trying to exploit one of those inefficient algorithms for factoring. But we haven't been able to do that. Whereas if someone came up with a downward self-reduction for factoring, then you would have that factoring is a unique end of potential line. So it would be in a class much lower than PPAD, which would be quite surprising. So what are open questions that this work leads to? So we'd like to think that in this work, we've initiated the study of downward self-reducibility in TFNP. Now, can we show DSR or circuit DSR-ness for more PLS complete problems? Or maybe problems actually lower than PLS, interestingly. There's reason to think that unique end of potential line is DSR, and that actually might be easy to show. More generally, it would be interesting to understand the relationship between DSR and circuit DSR for circuit problems. It's probably very hard, but if these notions are equivalent, that would be very interesting. Now, here's another open problem, sort of my favorite one from these. Another kind of self-reducibility that's very important is random self-reducibility, or RSR. Now, the definitions vary, but intuitively what it means is that given an instance, there's a way to solve it by querying, let's say, uniformly random inputs to the problem. And if you're given solutions to those ones, you can figure out the solution to the original instance. So like sort of a worst case to average case reduction. So many important algebraic problems that are in TFNP are RSR, right? Such as discrete log, RSA inversion, and so on. These are problems that are actually sort of weaker problems than factoring, as in lower in the hierarchy, because if you can break factoring, you can do those. So the question is, can you place RSR problems that are in TFNP in some subclass? So a very natural candidate to me seems to be the class PPP for pigeonhole problems. Sort of the reason being that the problems in TFNP that we know are RSR, such as discrete log and RSA, they are in PPP. So it would seem like maybe actually any RSR problem is in PPP. And the way to do that would be to exploit this very inefficient algorithm for solving RSR problems, but that is structured. And that algorithm is, given an input, like randomly sample some other inputs, get solutions to those, and so on. So maybe there's a way to show that those problems are in PPP. Great. I hope this was interesting. Thank you very much. And please read the paper if you are interested more. Thank you.